Alright, we're going to continue working molecular shape problems. We're going to do G and H on this run. G is carbon disulfide. So when we look at our valence electrons, again, we first have to total those. We have 4 here plus 6 times 2 here. 6 times 2 is 12 plus 4 is 16 electrons. So when we set this up, carbon is our central atom because it's listed first. So we're going to set the sulfur on either side. We're going to complete the octets of the attached species first. Any remaining electrons will go on the carbon. Well, when we look at this one, carbon, both the sulfurs are happy, but the carbon's not happy. So we have to get pairs of electrons to carbon. Now, I'm going to donate a pair from either sulfur. Carbon, double bond, sulfur, double bond, sulfur. We have 2 lone pairs left on each sulfur. So now everybody obeys the octet and everybody's happy. A side note right down here is we could also do it as a triple bond to a sulfur, and there would be 2 options, in which case we would have the resonance structures as they appear. Point being is when we do shapes, the resonance structures do not change. They only vary by the number of, or the position of the double bonds. So therefore we have 2 electron regions here for shape. We have 2 electron regions here for shape, and lo and behold, we have 2 electron regions here for shape. So when you're doing molecular shapes, unless you're asked for the resonance, you don't have to worry about them. Just pick one of them. It's not going to make a difference. So we've done our Lewis structure. Everybody's happy. So electronically, we have 2 electron regions around the carbon. So our electronic structure is linear. Our molecular structure is linear as well. Bond angles, well, they come from the linear, so there's 180. You can't move them any farther. And then that brings us to the polarity. When we look at the polarity here, we have 2 polar bonds. Sulfur and carbon are polar bonds, but they are perfectly symmetrical. So it's a symmetrical molecule shape. So these combined give us a non-polar molecule that contains polar bonds. Because remember, for polarity, we have to have polar bonds and lack of symmetry. Then that brings us to hybridization. Well, if we look at our hybridization, it doesn't matter which form we look at. We're going to need 2 singles, okay, 2 doubles, which we'll call later pi bonds. Singles, remember, are sigmas. We'll get to that later. But that means that these are the ones that can be hybridized. These have to be no hybridization. That being the case, then we have 2 bonds. So we're going to have an S and a P. So our hybridization for any form is SP. So we've done our hybridization for this one. So let's move to IF3, or iodide trifluoride. It's a little less complicated. They're all in the same family, so we have 4 atoms that all have 7 valence electrons. That gives us 28 valence electrons total. Iodide is our central species. Because it's listed first, we have 3 fluorides, so we're going to complete the octets. When we do this, we again fill all the octets of the externals first. At this point in time, we have 24 electrons in our Lewis structure, but we have 28. So any excess electrons get placed on the central atom, even if it causes to exceed the octet, because iodide is in the I believe the 4th energy level. No, 1, 2, 3, 4, 5th energy level. So it's n greater than 3, so it can exceed an octet. So at this point in time, we're going to start looking at regions. We have 1, 2, 3, 4, 5. So we have 5 electron regions. Now we don't care whether it's multiple bonds or lone pairs at this point. So that means that the shape is trigonal bi-pyramidal. So if we look at our shape, they're basically a triangle with an up and down axis. Remember, the lone pairs have to go in the triangle, so that means we have fluorine right here and here. Well, remember, lone pairs are like glass, so you can't see them. So what's the shape of this molecule? T-shaped. Sometimes it's easier to see this when you start off with model kits. Sometimes it's not. It depends upon the individual. But if you look at it, basically what we have is we're going to only see these 3 atoms here. We don't see the lone pair, so it's a T on its side. Alright, so we've got our T-shaped. So that takes care of electronic and molecular. So we need to look at the bond angles. Oh no. Alright, well remember, all of these will be 90 degrees here because they're perpendicular to the plane. That is the lone pairs. Now, again, you're not going to see the angles associated with the lone pairs, but I'm going to write them in so you can remember. This is going to be start at 120, but the lone pairs are going to push more, so it would make it greater than 120, which means these would be less than 120 on either side here. If you had 2 like fluorines here, then they would be compressed together. But because it's just alone, it's going to be 90 degrees to the other fluorines, and you're not really going to see. So if we were looking strictly at only the atoms, then we would have 90. I'm throwing in the lone pairs more to make sure that you understand who the pushier species are. Lone pairs push the most, then multiple bonds. So we got T-shaped. Our bond angles are over here. So we did the bond angles. And remember, the bond angles are a function of the electronic. That's where you get them, not the molecular. Now we've got polarity. We have polar bonds. And we know that because we have iodide-fluoride bonds. And let's be honest, who's the most electronegative species? Fluoride. So they're not going to be very polar, but they're still going to be polar. But overall, if the molecule is unsymmetrical, because look at it this way, we said it was T-shaped, and I'll put it right here. If I draw a plane of symmetry here, this side does not look like this side, so it's unsymmetrical. That being the case, this combines to give me a polar molecule. Making sure I'm still on the paper and you can see it. Okay, polar molecule. So then that brings us to hybridization. Well, remember, with hybridization we have 3 singles plus 2 lone pairs, and lone pairs can go in. These are going to combine to give us 5 hybrid orbitals. So all we have to do is count. S, remember we've only got 1 S. How many P's? 3. That's 3 plus 1, we're up to 4. We need 1 more, so we're going to go into our D's, and it'll be a D1. You don't have to put the 1, just like you don't put the 1 there, but some people like it because it helps them see. So now we've done the shape, etc., of G and H.